In the first video in this series, we introduced the concept of measurement error, where the measurements we take are not equal to the truth we wish to observe. While it may seem obvious that measurement error is a problem, the ways in which it can undermine our results are varied and complex. In this video, we will illustrate the potential impact of measurement error. Suppose we are simply trying to learn about the average caffeine intake of a group of people. If we ask people how many cups of coffee they drank that morning, we know that some will overestimate and some will underestimate the truth. Sometimes we might find that, on average, people are just as likely to overestimate as underestimate their coffee intake. When our errors balance out, we say the measurement error is unbiased. Helpfully, if we are only interested in average coffee consumption, then unbiased measurement error isn't a problem. While individual measurements may be incorrect, the group average would remain an accurate measure. If our errors are biased, however, then this will be a problem. If people are more likely to underestimate than overestimate their intake, for example, our group average will also be an underestimate. Often, we'll be interested in more complex analyses than just trying to learn about average coffee consumption. For example, suppose we wanted to study the relationship between caffeine consumption and blood pressure. One way we might investigate this is to gather data on caffeine intake and blood pressure for each person in our study. We could then plot a graph comparing these two variables. Our goal is to estimate the relationship between caffeine intake and blood pressure by fitting a straight line through our data points. The slope of this line conveys the strength of the relationship. A steeper line suggests a stronger relationship between blood pressure and caffeine intake. If caffeine consumption was measured without error, this would be a very straightforward analysis. But what if our measurements are inaccurate? First, let's assume that blood pressure is measured correctly, and see what happens if caffeine intake is measured with error. Suppose caffeine intake is subject to classical additive measurement error, meaning the observed values, the red diamonds, are equal to the unobserved true values, the grey circles, plus some random noise. Notice that the points have moved horizontally, some to the right, some to the left, but not vertically. This is because we assume it is only caffeine intake on the x-axis that is measured with error. This is how our fitted line looks if caffeine intake is measured correctly. If we fit a straight line using the points corresponding to the error-prone caffeine intake, it is less steep. An analysis using the error-prone data underestimates the strength of the relationship between caffeine intake and blood pressure. This can be surprising. Our data was subject to unbiased additive error. Our measurements were, on average, correct. This phenomenon is caused by the points in our graph being stretched out horizontally. This in turn stretches out our line, making it less steep. The underestimation is often referred to as attenuation. Some have suggested that attenuation is of limited concern, worrying more about overestimating the strength of a relationship. But underestimating the strength of a relationship can have serious consequences, such as causing us to overlook the potential of certain medical treatments or therapies. It is also not uncommon to think that measurement error always leads to attenuation. In fact, this attenuation only occurs in a very small set of circumstances. For instance, suppose in our caffeine example the measurement error took a different form. Perhaps people who drink more coffee tend to underestimate their caffeine intake, while those who drink less coffee tend to overestimate it. If we add these error-prone measurements to our graph, we would get a different result to the previous example. Here, our measurements are pushed more towards the center. This leads to a straight line fit that is steeper than if true caffeine intake was observed, overestimating the strength of the relationship. So far, we have assumed a very simple model and only explored the impact of error in caffeine intake on the slope of our fitted line. What would happen if blood pressure was measured with error instead? Well, now suppose caffeine is measured accurately, but blood pressure isn't. If we assume classical additive unbiased measurement error, our observed blood pressure measurements are these red diamonds. These red diamonds are vertically shifted, in contrast to the horizontal shift seen when coffee intake was measured with error. However, when we fit our line to these data, it looks similar to if the data were measured correctly. This is because of how our line is calculated. It focuses on the vertical distance between the points and the line. As long as the error in blood pressure is unbiased, then the errors will again cancel out and produce a similar line on average. While this may suggest measurement error doesn't matter if it is in our outcome variable, it still introduces greater uncertainty. The points are further from our line, which has implications for how much certainty we can have in our results. Again, however, if our error takes a different form, its impact will change. In this example, blood pressure measurements are more likely to be underestimated when the true blood pressure measurements are larger. This leads to an underestimation of the relationship between the two variables. The examples in this video are for some of the simplest scenarios. If we are interested in more variables or more complex relationships, then the impact of measurement error becomes increasingly difficult or even impossible to predict. We have also seen how the form of our measurement error plays an important role. Other error types discussed in our first video, such as multiplicative or Bergson, each have their own implications for analysis. Great care must be taken when predicting the impact of measurement error. We must be especially careful not to assume the generalizability of results that only apply in very specific contexts. If we want to avoid measurement error affecting our analysis, the ideal solution is to avoid measurement error in the first place. In situations where this is not possible, there are methods we can use to try to correct for the impacts measurement error would have. To do this, we will have to first learn about the type and size of the measurement error we are experiencing. In our third video, we will explore how to learn about our measurement error and what can be done to account for it.